So this was as a background, setup in which we can define delta hyperbolicity or Gromov hyperbolicity. Okay, so Gromov hyperbolicity will be delta hyperbolic for some delta. Okay, what does this mean? This is really what I have to define. So it's usually just called delta hyperbolicity, but that suggests it's dependent on delta, which sometimes is important, but we want to consider the situation where you just don't care what delta is, which is the normal case. Okay, so let's take a triangle. What is a triangle? So a triangle is, we have three vertices, P, Q, R. Okay, so we have P, Q, R in X. Okay, and we have sides L1, L2 and L3. But I'm deliberately not calling them PQ, QR and PR because, so Li are geodesics, because there is no assumption that the geodesic is unique. So geodesic metric space is one where geodesics exist. So we're looking at triangles in a geodesic metric space. We can look at triangles even in the general situation. Okay, but there should be a lot for these conditions to be useful. Okay, so definition here, we have seen this in hyperbolic space. So a triangle is delta thin if each side Li is contained in n delta of other sides. I'll write one of these conditions to make things clear. L1 is contained in delta neighborhood of L2 union L3, and two other similar conditions. Okay, so we've seen that this is true in hyperbolic space. So here are the examples. So one of the basic facts we saw in hyperbolic space is triangles are in fact thin, H. Okay, and we briefly saw the more extreme case of this, which is a tree. So I have a tree which is a graph without loops. It looks something like this. Now if I take any triangle in a tree, let me draw it. Well, one side will look like this and another side like this, and the third side would be an edge here. So this is a typical triangle. So in this case, in fact, delta equals 0. Okay, so this is a remarkable fact. Any side in a tree is contained in the union of the other two sides for a triangle. So this is the most extreme case of being delta hyperbolic, which is a tree. Now this definition turns out to be marvelous in that it holds for a very large class of spaces, and on the other hand it has very strong consequences. Most of the qualitative properties of hyperbolic space or trees are captured by these, and there are lots of them and many constructions can be made. But it's conceptually a bit limiting to have to restrict ourselves to geodesic metric spaces. It makes things a little clumsy. So we'll look at another definition which is equivalent, which does not require geodesic metric spaces. So an equivalent definition. So let's start this by looking at XD, so a metric space. Okay, so it's not necessarily geodesic. And so here what we'll do is we'll define the Gromov product. And this formula comes from looking at a tree. So let's look at a triangle in a tree. So here is a tree, and let's call these points X, Y, and Z. Okay, and let's look at that. Distance between X, Y is the red line. Distance between Y and Z is the green line. And distance between X and Z is the blue line. Okay, so now let's ask, what is this length? Well, I'll write down the formula for this length. In the case of the tree, it's very easy to see that this is distance between xz plus distance between yz minus distance between xy divided by 2. Okay, so this quantity is this length here. It's the length of the side between z and the nearest point projection on the geodesic from x to y. And this I'll call the Gromov product. So Gromov product of x and y based at z is this. You can write down this formula, and this makes sense. This is for any metric space. So what we have done is really just made a definition.